All right. So just a few minutes ago, I put up this one exam that everybody's definitely going to take, or else the final. Here's a practice final, and solution. Um, Although when I was going through old practice tests and trying to fit it to material that covering this semester, there wasn't as much in terms of material as I had hoped. So after cutting out questions because I didn't cover that stuff, there were only 8 questions left, which doesn't seem like a type of test that would fill 2.5 hours. And no, I'm not one of those instructors who gives an exam that's scheduled for a 2.5 hour slot and everybody gets done in an hour. I like to actually use the time, or have you guys use the time. Now, if you want to give up after an hour, that's your prerogative. And I will say that USM students give up on tests way, way, way too easy. But I did want to make sure that whatever I do cover this semester is covered on the final. So here are the 8 problems. And then I will include, like I do typically in my classes, my own formula sheets. So these are whatever you have, whatever is included here in a practice test is what will be provided to you on the real test. So things you don't have to spend time memorizing. But I would recommend that you are familiar with them to a certain extent anyway, just because if you're trying to dig it up exclusively from here, as if you've never seen it before, then no matter how few problems I put on this test, that's going to be a problem. So if I do add any more problems to this test, which I would do soon, I'll let you know. But this just gives you an idea of a type of problems that you'll see. There's a few that we haven't gotten to yet because they're about integration. Actually, yeah, these two, the last 2 problems are with on integration. So I'm going to definitely put on some more integration problems. But yeah, there's some interpolation. There's some floating point arithmetic or convergence. So it is comprehensive. I have done an oral final in the past, but it would be less practical in this setting with this many students and also 4 students that are not here. Okay. So that's something for you to look at your leisure. Now, as for what else is supposed to be submitted imminently, homework 3. So I've been getting a lot of questions. Not many people asking questions, but those who are asking questions are asking a lot. So that's something. But the point is, it's giving me a lot of material for the questions page. So I would encourage you to frequently check there. I don't think I put any up new today, but like yesterday there was a ton of them. Let's see, a lot of the 21 people in the class, I think 2 have submitted. So I'm expecting many more sparkling submissions soon, right? Right? Okay. We'll see. Okay. Now, do we have questions about anything on homework 3?
I have a question about like how you want us to submit it. So you were saying that you want us to just put everything in one document.
I'm not requiring that necessarily. I'm just saying that one thing that's kind of a pain is that when there's multiple files, especially if they are high resolution, like scans of paper and so forth, it makes it very difficult for my email program to download them. Especially if they're because sometimes like each page is like a 2 megabyte file, and I think there's actually a limit on how large a message USM's email server will tolerate. So, as a guideline, it's easier if you can if you have several images, you can paste them into Word documents. Some people have done that. So it expedites the grading process, if you will, if that is done. But I'm not. If you have technical difficulties on your end, I mean, you can submit however you need to. But I'm just pointing this out because it's something that will be appreciated. Also, and because certainly it's for only for large files that are problems. Like for instance, if you're going to have various M files, you can just go ahead and attach those regularly, or any diaries, any small files like that. I don't care how they're submitted. It's for large files that seem to cause a problem.
Okay.
How are concept checks being included, like quizzes weren't also so I just didn't know.
Oh, okay. Well, because really, a concept check is still part of a homework.
Okay.
It's just called a quiz because that's how Canvas implements it.
So it's included as part of our homework,
Right. Yeah. And so what I was doing was just giving 1 point per question. So the total number of points you got on all of those quizzes from section 6.1 to 6.5. So that number of points will be counted towards your homework 3 score. And then whatever else there was, all the explorations and exercises, so I'd like to do everything out of 100. I'll just make the explorations and exercises worth however many points to make it add up to something near 100. Let's see, I think there were 23, 29. Okay. I don't remember. We're probably talking 2 or 3 points each, roughly, for all those other things. Just like on homework, too. Any other?
In section 6.5, which is the
Yeah. Megan, I'll get you next. All right. 6.5. Okay.
Can you go to the third question? Yeah, this one.
Yeah.
So you said to produce a divided difference table in MATLAB.
Yeah.
And it has 3 inputs, which is x, y, and yp.
Yeah.
And yp is the derivative of the function.
Well, okay. Y is the vector of y values at the given x values, and yp are the derivative values also at those same x values.
Also at the same x values.
Yeah.
So do we need to compute the yp values before?
Oh no, you just like for testing purposes, you can just make them up, just like you would the x and y.
Okay. And one more question.
Yeah.
So we determine the number of x points in the divided difference table from the derivatives, yeah?
Wait, how many points?
I mean the number of x points in the divided difference table.
Oh, well, okay. How many x's you have? Because the number of the x's in the x vector, those are distinct. So for instance, let's suppose you have 4 x values. So then you also have 4 y values and 4 derivative values. But in Hermite interpolation, each x value gets listed twice. So you're going to have 8 entries in the first column of your divided difference table. So we were looking at like an 8x8 matrix.
But if let's say derivative is let's say second order derivative, then the x values have to be repeated.
Oh, no. In Hermite interpolation, you only have first derivative values. General oscillatory interpolation can have derivatives of any order, but Hermite is much more restrictive than that. Otherwise, for general oscillatory routine, that'd be, I'd have to become a very different interface for that.
And what is the use of yp value inside the function? Because we will be using the algorithm itself. So.
Well, okay. So what's going to happen is For this example for Hermite interpolation, after you list your have your x values, and you fill in the first entries, like there's that first loop that does the y values, but you'll do each one twice. Then when you get to the next column, then now because I mentioned you're modifying div diffs, and div diffs is just going to go through and subtract and divide. But what you can do is you can check, well, if the x values that you're subtracting are exactly equal, then you know that that's where you don't do that divided difference. You fill in a derivative value. Now, to be a little more concrete, if I go up to the algorithm for divided differences, okay. All right, so here you're filling in each y value twice. Here, only when on the first iteration through this outer loop, when j equals 1, only then do you have to do something possibly different. So at this point, you can check, are these x values that you're subtracting equal? That's when you would put in a derivative value. Also, the way this divided difference algorithm is structured, it's filling in, the columns are going from left to right, but within each column, it's going from the bottom to the top. So each time you put in a derivative value, you want to start from the bottom of that vector, like the end element, and then keep backtracking through it.
So if we have 8 x values and 8 y values, we'll have 4 yp values.
Okay. In the example I gave, if you're passed in 4 x values, you'll list each one twice for a total of 8 rows. And then, then you will put in 4 derivative values in that next column. It'll be entries, because what will happen is you'll have 8 y values, you'll have 7 total entries in the second column. So entries 1, 3, 5, and 7, the odd-numbered ones, will have a derivative. And then the ones in between will be ordinary divided differences. Okay. And Megan, you have some? Okay. Okay. Right.
What were we looking for, like the highest degree of the approximation?
No, because once you fill out the divided difference table, then actually construct a polynomial. Now, okay, one thing I want to point out, if we could go back to the Hermite example, even though this is not Hermite, but it's similar. When you make the polynomial, like you have your top row of divided difference coefficients, so you'll have constant term plus this times x minus this value, and then plus this times x minus this value times x minus this value, so in other words, it'll be squared. As points are repeated, you'll have linear factors repeated also. So it won't really become clear until you actually have a whole polynomial in front of you. And then it should ring a bell. Okay. Any other? Yes.
Exercise 4, I don't really understand what you mean by pseudocode or
I mean, you could write it out as actual code, but okay. Best example of pseudocode is what I have in all the algorithms in the book, using that kind of notation. Yeah. But like, I'm not looking for proper MATLAB syntax or anything like that. Yeah. I guess my working definition of pseudocode is something where it's not actual code, but if someone were to write code, then they'd have a pretty easy time doing it in whatever language they were using. One thing that came up, a question about exercise 3 that unfortunately I had not made clear in the problem statement, so I added this detail. When you're estimating the error, it's most helpful if you're actually estimating it on a particular interval, and ideally an interval that contains the interpolation points. So you're estimating the error for the polynomials from exercises 1 and 2 that are using interpolation points in the intervals 0 to 3 in both problems. So that means estimate the error on the interval 0 to 3. Like we have the unknown point in the error has to be in that interval. You assume that x is in that interval also, because that's actual interpolation. If you wander outside of that interval, so away from the interpolation points, that's called extrapolation, which is generally not very accurate at all. All right. Any other?
For exercise 10, once we get the Chebyshev points,
Yep.
how do we, I guess, use those to graph?
Oh, okay. Well, really what you would do is, okay, so in other words, you're getting a polynomial, but, really, this actually applies to both polynomials. Once you have a polynomial, it's like it's vectors of coefficients, then what you should do is do, actually similar to a function you did back in homework 1, graph poly. In fact, if you did that from homework 1, you can just go ahead and use it. Because what does that function do? It creates a vector of many equally spaced points, like 100 equally spaced points, and then uses your polynomial, because you have coefficients, and polyval to plug in all those x's and plot them. Because if you only use the interpolation points for purpose of producing a graph, it's not going to be a smooth curve. Well, doing well in time. Any other? Okay. Oh, one public service announcement in general. You probably I'm sure you got reminders about this already, but apparently they're taking SOAR down tomorrow for some upgrade, and it's going to be down for like 5 days or so, which is going to annoy the hell out of me. But so if there's anything you wanted to do in SOAR, you might want to get it out of the way quickly. Okay. Now, so now that we're finally making use of polynomial interpolation to solve problems for calculus, and we've been using that to produce approximations of derivatives, and just starting to discuss definite integrals. So, like, just very bare bones last time. Like, here's the general kind of approximation we're looking for. What is a quadrature rule? And also, and so the idea is the approximation of the exact integral of f of x is the exact integral of the approximation, I should say polynomial approximation, of f of stop it. Okay. So in other words, actually, I can try to phrase this a little more succinctly. So the approximation of the integral is the integral of the approximation. And the form we're using is a polynomial. Also, one very important point from what little we've seen so far in this chapter is to obtain an approximation scheme for, it doesn't matter whether it's differentiation or integration, based on combining values of f of x. What we do is you solve the appropriate problem on the Lagrange polynomials. So in other words, what we saw was if you're trying to approximate a derivative at x naught using points near x naught, then you actually compute the derivatives at x naught of Lagrange polynomials for those points. And if we're combining function values to produce a definite integral, then the way in which we combine those values, the coefficients, also known as weights for integrals, then the problem we're trying to solve for f of x, we go ahead and solve that problem for the Lagrange polynomials. So derivatives or integrals of Lagrange polynomials are extremely helpful for derivatives and integrals of general functions. All right. So what we're going to look at today is specific examples of interpolatory quadrature rules that are called Newton-Cotes rules. Really invented primarily by Cotes, not Newton, believe it or not. Even though nobody knows who Cotes is, but apparently we should have. And the idea is that the nodes are, in other words, points at which we evaluate f for integration are equally spaced. But the thing is, Newton-Cotes rules are only a starting point. We need to be a whole lot more sophisticated because we're going to have two competing criteria. We can get integrals as accurately as we want if we don't care about efficiency. We can get integrals as efficiently as we want if we don't care about accuracy. But in this field, you really, really care a lot about both. And so it takes some ingenuity to develop approximate integration schemes that meet both of these criteria, and for as wide a variety of functions as possible. Okay, so we're starting with simplest techniques today, and then we'll get to the more interesting ones toward the end as we get down to the end of the semester. Okay, and then those integration techniques are a springboard for a great many techniques. Well, like I use them often for solving differential equations, mainly. Okay, whether it's ODEs like you saw in Math 285, or PDEs like are taught in Math 417, for example. Okay. And of course, if anyone has thinks of any questions about homework 3, they're welcome to interrupt. But in the meantime, more about integration. So a quick recap. The most important points for integration last time interpolatory quadrature rule is that the integral is approximated by a sum of f evaluated at certain points. These are nodes. And then they're multiplied by coefficients, which are called weights. And when it's interpolatory quadrature, we have a form. The idea is we can choose the nodes however we want, but the weights, once you choose the nodes, the weights are set in stone effectively. Those are the integrals of the Lagrange polynomials on AB. So, all right, so to get the terminology straight, those are the nodes, the x's, are for weights, just so you know what I'm talking about, because I'll bring these terms up all the time. And then okay, need to be in math mode for that. Those are the Lagrange polynomials for whatever nodes we choose. Okay, so the idea is we're picking n points, and generally these points will be chosen to be within AB. Now, you might think, well, why would we not do that? If we're integrating on AB, then of course we should choose points in AB. And in fact, the definition of a Riemann integral requires that these points are in AB. But there actually are exceptions to this. We just won't get into them now. So for now, we can go ahead and assume that we're choosing points in AB. They can include the endpoints. That's actually quite common. And then because we're choosing endpoints, when you interpolate at endpoints, the degree is n minus 1. So that's why I have this notation here for Lagrange polynomials of degree n minus 1 for these points. So, and recall, Lagrange polynomials are equal to 1 at one of these points and 0 at all the others. Okay. Actually, I want to put this onto a new page. Okay. So this is the definition that I gave last time, but I didn't give any examples of actual Newton-Cotes rules. So that's what I'm going to do now, or interpolatory rules. So that's what we're going to do now. So a Newton-Cotes rule it's a type of interpolatory quadrature rule, but it has this one particular property on top of being interpolatory, that whatever nodes you choose, they must be equally spaced within the interval AB. All right. Now, what I'm going to do here is give you some Newton-Cotes rules of very, very low degree, but a lot of other techniques are built on top of these. All right. So okay, so the first and I guess simplest Newton-Cotes rule. I'm only choosing one node, so n equals 1, and my one node is equal to the midpoint of A and B. And there's only one weight, and that's going to be the length of the entire interval, B minus A. One thing I'm going to point out is, however many nodes we have, the sum of the weights, so in this case it's x1 and w1, the sum of the weights is always going to be B minus A. And the reason for that is the integral, because if you have all the weights, the sum of all the weights is the same as the approximate integral of 1, because if I set f of x equal 1, this sum here is just the sum of the weights. Well, what's the integral of 1 from a to b? It's b minus a. Yeah, the integral of 1 is always the difference of the limits. So we should certainly be accurate for a constant function. Otherwise, what are we doing here? So, so the sum of the weights will always be b minus a. So in this case, we just have that one weight. And this particular rule is called the midpoint rule. Okay. So what I get is so it's approximated by b minus a times the value of a function at the midpoint, a plus b over 2. Okay. All right. Now, actually, what I'm going to do is, when I state these, I'm going to say it's exactly equal to this, and also include the error term. So the error is f double prime at some unknown point, and then we have a b minus a cubed, and unfortunately I'm forgetting the constants. Well, I'm going to make a guess at it, and then I'm going to go actually look it up in the text. So I think it's 24, but let's see. All right, chapter 8, Newton-Cotes Rules. Okay. Oh, wow, I got it right. Okay. Yeah, so it's the second derivative unknown point times b minus a cubed. Now, the thing is, what that means is if the interval AB is large, then of course the error could be large. But what do you expect when you're approximating an integral by only evaluating the integrand at one point? But like I said, these rules are meant to be like foundation for more sophisticated ones that'll be much more accurate. Okay. Now I'm going to define one very important term here. The degree of accuracy is the degree of is the highest degree of polynomial that can be integrated exactly by this rule. So for the midpoint rule, the degree is equal to 1. So what that means is any polynomial of degree 0 or 1, if you apply this rule to it, it'll be integrated exactly. Now, generally, whatever n is, the degree is going to be at least n minus 1. But here we get one more than that. And it's because of the symmetry. When you evaluate it to midpoint, because you choose the midpoint, the like leading error terms cancel out. So you get a little more accuracy than you would expect. Because if you approximate by a polynomial of a certain degree, you might think that's you'll only be able to get polynomials of that degree or less integrated exactly. But symmetry gets you something more. And that makes sense because if you have a polynomial degree 1 or less, a linear function or a constant function, its second derivative is 0. So the error would be 0. Okay. All right. Okay, so I'll make a comment here in writing. For an endpoint rule, or n-node, stop it, n-node rule, the degree is at least n minus 1. And later we'll see how we can try to get the degree to be as high as possible. Yeah. All right. So that's one rule, the midpoint rule. The next one is the trapezoidal rule. So here we have two nodes, and the nodes are just the endpoints. X1 is A and X2 is B. And then the weights W1 and W2 are equal. They're both equal to B minus A over 2. So that way they'll add up to B minus A. So the reason it's called a trapezoidal rule is because instead of using rectangles like you did at the beginning of Cal 2, the area of a curve is approximated by the area of a trapezoid. And the area of a trapezoid is equal to the base, which is B minus A, and then you take the average of the heights, which are given by f of A and f of B. So you divide that by 2. So this is the area of a trapezoid with heights f of A and f of B, and the base is B minus A. So that's the approximation, and then the error term is actually negative. Okay, so we have minus f double prime over 12 times b minus a cubed. So very similar to the error term for midpoint rule, but notice it's not as accurate. The error is minus 2 times the error for the midpoint rule. So it's interesting, more nodes leads to still a little less accuracy. But still, these are pretty comparable in terms of their effectiveness. Now, in Cal 2, it depends on the instructor whether they actually take the time to cover approximate integration, because a lot of calculus books have a couple of rules. There's a composite trapezoidal rule where you divide A, B into subintervals, and you use this on each one of them. And I'm going to cover that, actually, out of curiosity, I'm going to check here. Coming up soon. Oh, Thursday. Yep. Okay. All right. So, so on such small subintervals, B minus A is small. So then the error is small. But okay. So the degree of accuracy is also 1, which you can tell from the derivative here. It's second derivative again. Okay, and then one more comment I want to make about each is, since we're doing, these are interpolatory quadrature rules, in the midpoint rule, you're approximating f of x by the constant function f of x, or p naught x is just equal to f of m, where I'm going to use a notation often m is the midpoint of a and b. So this is 0 degree polynomial interpolant. Whereas in the trapezoidal rule, we're approximating f by the line passing through the points a and b. So if you were to come up with the equation of this line that passes through those 2 points, take that as your f of x, integrate that, that would be that would give you the trapezoidal rule. Okay. Bless you. Okay. Now, one more Newton-Cotes rule. Simpsons rule. Okay, so in this case, n equals 2. We're using a second degree polynomial to approximate f of x. So now we have 3 nodes. So we have, actually we're taking like the union of the nodes for midpoint and trapezoidal. So we have A, x2 is the midpoint, and x3 is equal to B. And then we have, for the weights, the first and third weights are equal. We're equal to b minus a over 6. And then the last middle weight, W2, is equal to 2 times b minus a over 3, or 4, 6. So it's kind of strange that that the weights are not equal. So even though the nodes are equally spaced, the middle one gets 4 times as much weight as the ones on the ends. And I'll talk about that in a moment. But first I want to state the actual Simpsons rule. Okay, so that'd be b minus a over 6. Okay, and what I have in between is f of a plus 4 times f of midpoint, a plus b over 2, plus f of b. So here, it's easy to see here, the middle point is getting 4 times the weight of the endpoints. And then the error is negative again. And it's the fourth derivative at an unknown point divided by 90 times b minus a to the 5th power now. So if ab is a small interval, then that error is going to be a whole lot smaller. So generally, Simpsons rule, most of the time, I won't say all the time, much more accurate than either trapezoidal or midpoint rule. And the degree of accuracy is 3. So in other words, any cubic polynomial will be integrated exactly by this rule, cubic or less. So the idea is we're approximating f by a parabola passing through these 3 points at x equals a, f of m, which is the midpoint, and b. So if you were to pass a parabola through those 3 points on the graph of f, and then integrate that quadratic exactly, then that is Simpsons rule. Okay. So these are the best known examples of Newton-Cotes rules. So in all cases, the nodes are equally spaced, and the rule just comes about by integrating a polynomial passing through the graph of f at these nodes, integrating that exactly. Okay. Now, so before I actually, I'll go ahead now and if there's any questions about any of these. I'm going to go ahead and illustrate them. So let's work with the interval 0 to 1. And I'll let f of x be e to the x. What's the exact value of this integral? From 0 to 1. E minus 1. Yeah, because you get e to the x, the antiderivative. You plug in the limits, you get e to the 1 minus e to the 0. So it's e minus 1. And for convenience, all right, so e minus 1 is 1.718281828. one thing I want to point out before I go on, since we're dealing with E. Okay, so we look at the decimal expansion of E. Now, I'm sure that at least some of you every year at least observe Pi Day, March 14th. Okay, and of course, a few years ago it was very special. It was March 14th, 2015. But the thing is, with E, it's a little harder to do because you look at decimal expansion. That best you could do is like February 7th and get 2 decimal places accounted for. But February 7th of 2018 is the best E day that we can have. So next year, maybe we'll have a Siam chapter observe it or something. So maybe we'll have eclairs or something. I don't know. So no, I think that E is a very important number too. It's not as popular as pi, but it should get at least some recognition. So next year I'll talk to Haley Dozier and see what we can do. Okay, so here's the exact value that we're shooting for. So if we try the midpoint, then the approximation would just be, well, it would just be b minus a, which is 1, and then we're just evaluating f at the midpoint, which is 1/2. So that's going to be, all right, so 1 times e to the 1/2. So that's going to be 1.6487212. Okay. All right. So of course not so great, but we're just using 1 point. Now let's try trapezoidal. So that would be b minus a over 2 times times e to the 0 plus e to the 1. All right, so now if I go ahead and compute that, so that would be e plus 1 over 2. So 1.859. All right, so a bit of undershooting here, overshooting here. Midpoint turned out to be somewhat more accurate, at least. But now let's try Simpsons. So that would be b minus a over 6 times f of a, which is e to the 0, plus 4 times e to the 1/2, plus e to the 1st. So let's see what that turns out to be. So that would be 1 plus e to the 1/2 plus e to the 1st, all over 6. Something went wrong. Oh, what did I forget to do? What? I forgot to 4. I need to multiply. I had to multiply the middle value by 4. Okay. Much better. All right. So now if I take that, as we can see, we got the first few decimal places correct. So indeed, we saw that it was much more accurate than the other two. But what happens is you're evaluating at more points. And believe it or not, what we're going to see before the end of this chapter is that it seems, based on the error alone, that trapezoidal rule would be the worst of the 3. But there are certain kinds of functions for which it is far away the best. And then there's other techniques that we'll see very different from these that are generally better. Okay. So any questions about what happened in this example? So So of each rule, you have the nodes are prescribed, and then the weights are obtained from integrating Lagrange polynomials. And then, so at least in this case, the weights have been figured out. We could just go ahead and use them. And then you're just plugging those nodes into F, multiplying by the weights and adding up. And there you have your approximation. Okay. All right. I haven't gone into, it's discussed some in the text, where these error formulas came from. Where they come from is, you take the error formula that you've been dealing with in this latest homework for interpolation, and you take the integral of that error formula. Now, that can be a real pain to work out in certain cases, especially since you're trying to deal with an unknown point, so you're settling for not fully formed expression. But that's the basic idea. What we can say is the error in the integral is the integral of the error, and by that I mean interpolation error. Okay, so I could run with this. The error in the integral of the interpolant, because that's what we're doing. All of these rules are defined by taking a polynomial interpolant of f, and then we're integrating that exactly. So this is the most succinct way in which I can describe how we get these error formulas. Okay. But that'll become more important next time when we start looking at composite rules. Because with derivatives, we had some spacing h, and we would describe the error in terms of powers of h. We don't have that with integrals. Not yet, but on Thursday we will. Now, okay. So, actually, I don't know if I've picked out the problems yet. Oh, no, I've not yet chosen the problems for this section. There's some that involve writing short MATLAB functions, and I emphasize short, that actually implement these rules, midpoint, Trapezoidal Rule, and Simpsons. Or a general Newton-Cotes rule. In this part, which I haven't gone over here, it's discussed how to come up with the error formulas. I'll admit, it's kind of nasty. Okay. Now, okay. So I mentioned earlier the accuracy of an interpolatory rule is at least n minus 1. And here's a more general statement that can be made, that if n is odd, for example, in the case of the sorry, I goofed here. N should be 3 in this case for Simpsons rule. Okay, that's a total number of nodes. All right, if n is odd, that's when you get extra accuracy. That's when the Newton-Cotes rule delivers a degree of accuracy that's equal to n. Otherwise, if it's even, you settle for the lower bound of n minus 1. So these rules, the Newton-Cotes rules with odd numbers of nodes, are more effective. And it's because of getting some error terms to cancel because of the symmetry. The fact that these nodes are equally spaced is important. Okay. Now one thing that's quite unfortunate, though, is if you'll notice, the way I've defined a Newton-Cotes rule so all of these rules that I've shown you, midpoint, trapezoidal, are very low degree. So why not just use high degree Newton-Cotes rules? Because we've already seen that of all the rules that I've shown you, the one that was highest degree was the most accurate. The Simpsons rule. So you think, okay, let's just keep going with that, keep running with that. If we just increase n, the number of nodes, then we can get as much accuracy as we like. Well, no, it doesn't quite work that way. And so I'm going to do an example to show you. Okay. Actually, I want to see what code I have on hand to help me do that. Okay. I'm going to show you this function. Okay. So what this function does is I specify a vector of nodes. And the nodes are in the interval -1 to 1. And the reason I do that is I use this generic interval. And that way, if I'm actually trying to integrate over a different interval, AB, then I can always take these weights and scale them to whatever interval AB I'm working with. So what I do here is for each of these nodes, I need to get the corresponding weight. So what I do is I make a Lagrange polynomial for that node that's equal to 1 at the node and 0 at all other nodes. So I'm cheating here and using polyfit to do that. Now, as I said at the beginning, what are the weights? The weights are the integrals of Lagrange polynomials. So I have MATLAB help me integrate those Lagrange polynomials. I use polyint, that gives me the antiderivative coefficients, just using a power rule. And then I substitute my endpoints, 1 to -1. So here, this is indefinite integration. That's what polyint does. And then substituting in the limits gives me the definite integral. And those are my weights. Bless you. Now, I'm going to show you an example where a high degree Newton-Cotes rule fails. And this is an example you've actually seen before. It's not even going to be that high degree. Okay. Now, I'm going to let f, my integrand, I'll specify a function handle, be 1 over 1 plus x squared. Where have we seen that? What's the name of that example? Runge's example. I'm using dot here because I'm going to pass vectors into this function. Okay, so that's my integrand. My x values will be, from that example, -5 to 5, equally spaced. Okay. So what I'm going to do is, if I want to try a Newton-Cotes rule, the easiest way to do that here in MATLAB, since I want to try an 11-node rule that uses these points. Now, I don't know offhand the weights for a rule like that. But here's what I could do instead. To simulate Newton-Cotes integration of 11 nodes, what I can do is find a polynomial interpolant of f at the nodes, which I have here. So I'll go ahead and do that. So my polynomial p is polyfit, and I use x, and then I use f of x for my y values, and then the degree is going to be 10, because I have 11 nodes altogether, but degree needs to be 1 less. and then integrate the interpolant on the interval AB. Like I showed you in that function where I do that with the Lagrange polynomials. Okay, so the integral of P is polyint, and then I substitute the limits. So, so what we have is my approximation is going to be polyval of the integral at 5 minus the value at minus 5. Okay, so here's our approximation. Now, that doesn't mean a whole lot because we have no idea what the exact answer is supposed to be. Let's get the exact answer. Our function, recall, it's 1 over 1 plus x squared. What's the integral of that? Or antiderivative of 1 over 1 plus x squared. Something you were definitely taught in Cal 2. It's arctangent. Great. So the exact is going to be arctangent at 5 minus arctangent at minus 5. As you can tell, it's just a bit off. Okay. So why is that? Well, we've already seen that the polynomial interpolant of f on this interval using these points is terrible. So, so of course, if we're approximating the integral of f by integrating exactly a function that poorly approximates f, then the result should be also a poor approximation. Now, as far as why that failed, from a integration quadrature rule point of view, I'm going to show you the weights using a function I showed you. I just have to pass in the nodes. So the nodes they need to be for the interval minus 1 to 1. So I'm going to take my x values, which are minus 5 to 5. I'm going to divide them by 5. So this gives me equally spaced points in the interval minus 1 to 1, which is what my function expects. And then what I would do is I would take these weights and just multiply them by 5 to get the weights for this interval. Well, let's look at those weights. We have some negative ones. That's a problem. So it's because we can get negative weights. And why is that bad? Well, quadrature rules, you're basically approximating the integral using rectangles. The heights come from the values of f at the nodes. The weights come from the widths of your rectangles. And the widths of those all sum to AB. So having negative weights is going to really throw things off. So in fact, it has been proven Newton-Cotes rules have at least one negative weight for all values of n, at least 11. I've actually found that even a little bit before then, like I think around 9 or so, n equal 9, you can get a negative weight. But the statement in many textbooks is for all n that are at least 11, there's going to be one negative weight. So in other words, do not use such rules. Never, ever, ever, ever use a quadrature rule that has a negative weight. It's bad news. And as we just saw, how from how poor this approximation is. Now, on the other hand, if I use, actually, out of curiosity, I'll bet I could do better just using Simpsons rule. So if I do, well, the width of the interval minus 5 to 5 is 10. So if I just use Simpsons rule, which has positive weights, so b minus a is 10 over 6 times f of 0, no, sorry, f of the left endpoint plus f at the midpoint times 4 plus f. I have 5 minutes. Why are y'all packing up? Plus f at the right endpoint. Ooh. That's even more horrible, if you can believe it. Unless I did something wrong, which is entirely possible. because the exact value is only that. Okay, but again, this is a node that this is a rule that has only 3 nodes, so I wouldn't really expect much accuracy. Okay. Well, all right. One more thing I'll try is instead integrate using Chebyshev points on the interval -5 to 5. So what I do is my x values will be cosine, and I want 11 points altogether, just like in the previous attempt. Okay, so 1 to 11 times, okay. All right. Oh, wait. Sorry, I got my formula mixed up. Okay. So, actually, I want this to be a column vector. Okay, it's a little easier to see. Okay, so here are my points from -1 to 1, vis-a-vis Chebyshev points. So these are the roots of the Chebyshev polynomial of degree 11. Okay, although these might have been messed up a bit. Actually, I think I did mess them up. Hold on. Okay, so then I get 1 to 21 over 22. Yes, okay, these are the right ones. And then the scale to -5 to 5. Okay, I have 2 minutes. Okay, so now what I do is I go ahead and use polyfit at these points, and then I integrate that polynomial exactly. Okay. All right, and we get 2.83 for our approximation. Compared to the exact value, a whole lot better. Still not great, but it certainly beats these Newton-Cotes rules. And I should mention, it's not something I really cover here, but so interpolatory quadrature, actually I'll type this in the notes. Okay. Interpolatory quadrature using the Chebyshev points as nodes that are scaled and shifted as needed to the interval AB, because Chebyshev points are -1 to 1, is called Clenshaw-Curtis quadrature. So this is actually one of the best integration techniques out there, taking advantage of the very nice properties of a Chebyshev rule for minimizing interpolation error as the effect of reducing quadrature error as well. Okay. Now, okay, I'm out of time. One thing I want to explain, I will on Thursday, is why is it for Simpsons rule that middle weight is so much more, 4 times the other two? So that's something I'll get to on Thursday. So keep any homework-free questions coming, because I'm sure that's what you guys will be doing this evening. Sorry to ruin your evening, but should have started sooner and spread out the pain a little bit. So I'll be watching for those submissions. Oh, okay.
And also,